Hey, I found the motivation to make another video, but there is a ridiculous amount to cover today, so we're not going to waste any time on an intro. It's great, and when I say it's great, I mean it's kind of terrible. Before the video really starts, I need to take a second to thank my two biggest supporters. Mom and Dad, you are the true enablers of this project. You've provided me funding, a space to set stuff on fire, and most importantly, motivated me to never stop building. I hope you enjoy watching this video as much as I've enjoyed making it. Alright, super quick, what are we actually doing today? A ton of stuff. Test stand V1, V2, and V3, rocket avionics, rocket recovery, and enough motor static fires to warrant a National Guard response. Specifically, we're covering three main topics: motor improvements, test stand improvements and static fires, and flight vehicle development. Let's get started with the most critical thing on the list, motor development. As much as I loved the last motor, there were many improvements to be made. For example, these set screws are going to drive me insane. The nozzle is mild steel and is being slowly corroded away by moisture and exhaust products. There's no real way to attach the motor to a test stand or a rocket, and the expansion ratio of the nozzle is straight up wrong. What's an expansion ratio? Every nozzle has an expansion ratio that determines how much the exhaust will expand by the time it exits the nozzle. This expansion also changes the pressure of the exhaust gas. Ideally, the exhaust gas leaves the nozzle at the same pressure as the atmosphere. This is called optimal expansion ratio. If the expansion ratio is too large, the exit pressure is less than atmospheric pressure, causing the exhaust to be squeezed by the atmosphere. It's also possible for the expansion ratio to be too low, making the exhaust underexpanded. As you probably could have guessed, this means that the exhaust pressure is higher than atmospheric pressure. Both of these situations will make the motor less efficient, so we would like to be as close to the optimal expansion ratio as possible. And now you know! With all these new improvements in mind, I cooked up a better motor with the help of Peerless Pattern. These guys have some seriously cool, highly precise CNC machines that were used to make this motor. They sponsored the material and the machining to make not one, not two, but three new motors. Thank you, Peerless. This project would not have been possible without you. Now back to the motor. The new motor checks every box in terms of improvements. The nozzle is 316 stainless steel, so it won't rust or corrode over time. The upper bulkhead does have a convenient way to mount things, or mount two things, with this handy-dandy threaded section. The nozzle ratio is actually correct, and the precision is much higher than what I could get on the manual machine. And the set screws, well, just look at them.
Nice.
Every part of the motor is substantially more robust than it needs to be, and should handle the extreme loads of testing with no problems whatsoever. Foreshadowing is a narrative device in which future events are hinted at prior to their occurrence in the story. A better motor necessitated a more advanced test setup than two planks of wood clamped together in the driveway. That is an extremely low bar, so I'm confident that this is an improvement. Enter test stand V1. It works in the same way you think it works, a little scale connected to a giant lever. When the motor fires, it pushes down on one side and lifts up the scale on the other. Unfortunately, having the capability to measure thrust is only useful if you can actually produce some in the first place. Creating an effective fuel mixture was a particularly painful process that took a long time and was honestly not at all interesting to watch. Most of the test fires just sat there and fizzled out. Once I did manage to concoct a mixture that actually did something resembling a firing, I became aware of the extreme inadequacy of my testing setup. The only real way to get data was to estimate the reading of the spring scale from the video and then plot that with respect to how many frames had passed. This is amateur. I needed better data. So, after a few more static fires, I set about improving things once again. Test stand V2 is an improvement over test stand V1 in every single area. Most importantly, it has a digital load cell so that I can collect high-quality digital data over the duration of the burn. Secondarily, it has screw terminals so that my electronic ignition system will integrate more easily. And finally, it's designed to be adjustable so that I can test motors that are of different lengths and diameters to this one. So what did I see with my more sophisticated test equipment? That the fuel still sucked. In fact, it sucked so much that it didn't even want to stay on the test stand. failure was unfortunate, but, as my dad would say, data is data. So, I used the data I gathered from the failure to improve the test stand and test procedures. I built a new structure to hold an updated shield system around the test stand. Next, I focused on creating a procedure that would allow me to reliably produce less volatile fuel. The old end-burning fuel grain design was ditched for a far more standard radial burn geometry, designed to burn more quickly. I theorized that this geometry would synergize with a calmer fuel mixture and put me right in the sweet spot.
3, 2, 1. Whoa. Okay. 3, 2, 1.
At long last, I had a process to produce fuel that performed reliably. The motors did not produce quite as much thrust as I had calculated, but I'm happy to trade thrust for consistency in this case. Here's the data from the most recent test fires. Each motor burned for roughly a quarter second and produced peak thrusts of between 160 and 212 newtons. Specifically, test 1 in blue produced 165 newtons, test 2 in yellow produced 160 newtons, and test 3 in red produced 212 newtons. In my opinion, these numbers are acceptable for now, but in the future I plan to get these motors to perform even more consistently. Additionally, I'm planning on upgrading my load cell data collection system to be able to sample data at a higher rate. That way I have a better quality thrust curve than my mere few points that I have now. That about wraps up everything that's changed on the motor and test stand side of things, so let's transition to the next order of business, the rocket. The rocket is going to be under serious load due to acceleration, so I tried to design something that would be both robust and lightweight. The outer structural frame of the rocket is made of a thick-walled cardboard tube, and the inner components are held together with a 1/4-inch thick steel threaded rod. The steel rod runs all the way from the motor bulkhead through the avionics bay and up to the parachute connection point. This design should be strong enough to survive while still being as light as possible. It would be nice to get this thing back on the ground in some format other than a giant pile of plastic and fasteners, so I built a parachute system. Usually, model rockets use a small black powder ejection charge to kick the chutes out of the rocket so that they can open in the air. The challenge here is that since I'm building my own motor, I do not have the luxury of a pre-built ejection charge, and I would like to minimize the use of custom pyrotechnics as much as possible. Thus, I made up my mind to attempt designing my own way to deploy the chutes mechanically. This proved challenging. The main problem here revolves around how to get the chutes out into the air and away from the vehicle so that they will inflate. After brainstorming and generating several ideas, I selected this one to prototype. The idea here is that when the rocket reaches apogee, or the highest part of the flight, a servo will open this latch and the two halves will separate. Then the parachute will be released into the air and everyone will live happily ever after. Having a mechanical parachute system is great and all, but how does the rocket even know when to deploy the parachute?
Avionics.
The most reliable method to do this, in my opinion, was to stuff a little computer into the rocket and then have that figure out when to deploy the chutes by listening to a combination of accelerometer and barometer data. A nice bonus of doing this is that we can also log all of this data throughout the flight and analyze it later. So, I need a small, portable computer with a bunch of sensors and some way to store data. Okay, it looks like my phone won't work for this, but if anybody wants to send me theirs, I'll be happy to try it out. The real solution? I present to you the Raspberry Pi Pico, and a few of its friends, the SD card module, the gyro plus accelerometer, the backup high G accelerometer, and the barometer plus temperature sensor. Together, with a bit of code, this pile of boards will act as the brain of the rocket. And here's what it looks like when it's assembled. It's not the prettiest thing in the world, but it should work for a few flights at least. In the future, I plan to overhaul this entire system and reduce it down to a single PCB, but that's going to be an entire project in its own right, so I'm sticking with this for now. With that said, pretty much the entire rocket has been built at this point, and it's time for integration, the part where everything always works exactly as planned first try. In case you couldn't tell from the title, this is the part where things do not work first try. Pretty much every system here has some slight issues that need to get sorted out in order for everything to be working together in harmony. This is also the part of the video where I tell you that getting this thing in the air is very much a work in progress. Turns out rockets are hard, go figure. Hopefully in the next video I'll have some cool flight footage to share, or at least a good angle of a cataclysmic failure. Until then, I've been Moses, and I'll see you next time. This is the outro. This is the outro. I have a green screen room for another 30 minutes, so I'm just doing random things until my time expires.